Okay, we recently did constructed confidence intervals for P, the population proportion. Now we're going to construct confidence intervals for mu, which is the population mean. Okay, and for P, we use P hat. For mu, we're going to use X bar as the estimate for mu. Okay, so to construct a confidence interval for mu with sigma known. Okay, so if we know the population standard deviation, here our margin of error is z sub c times sigma over square root of n. Thinking, well, gee, I've seen that before, the sigma over square root of n. That is the standard deviation of the sampling distribution of sample means. Okay, that's sigma of x bar. So our confidence interval is x bar plus or minus z sub c times sigma over square root of n. So we can interpret it in these two ways, okay, which I'm not going to read those to you. To use the z-scores for z sub c by the central limit theorem, we must have either an approximately normal distribution to start with, or we need a large enough sample size. And the general stipulation is that the sample size is greater than or equal to 30. Okay, so again, in order to use this whole idea, we're going to have to make sure we have a normal distribution to start with, or a large enough sample size. Okay, so as we go through the first example here, okay, this is basically plug and chug, just like it is for the proportion. Construct a confidence interval for mu, given the following information. Okay, so I give you a 95% confidence level, a sample mean, a population standard deviation. Okay, so that's going to be important here. Okay, the sigma is 0.8. That goes up with this idea here that sigma is known. Okay, so when we use our formula, we're going to plug in the values for x bar, z sub c, sigma, and square root of n. So when you do that, again, it's just plug and chug. X bar, they told us, 31.39. Z sub c, so we're 95% confident, so that's your 1.96. Remember, that's the middle 95%. Okay, so if you need to go back and review that, go ahead. And then sigma's 0.8, and then standard deviation, I'm sorry, square root of n. N is 82. Our sample size was 82. So the margin of error there, 0.173. Add and subtract that from our sample mean, and we get our interval estimate for mu. So now notice that mu is now in the middle. Before, P was in the middle, okay, our population percentage. So now we're just looking at mu instead of P. Okay, on our calculator, okay, similar to using the calculator to find a population proportion, a confidence interval for a population percentage or proportion. Okay, so same idea. We go to stat, test, we choose z interval. Okay, so let me just show you real quick on the calculator. Okay, stat, test, and then scroll down to z interval. Okay, now you just got to be careful. Z test we're going to use later on in the course. T test we'll use later on. Okay, a lot of these we're going to use later on, so you have to pay attention that you're on the right thing. Okay, so the right type of test. Okay, so we choose the z interval and then just enter our values in. Now we have to recognize here the first step is a little bit different. It says data or stats. What data is, if you were to list values in list 1 or list 2, that's where you put data. Stats means that we're given the statistics. In this question, we were given x bar and sigma, so we were given stats. So that's what we want to make highlighted for this one. Okay, the standard deviation was 0.8, so I have to change that to 0.8. The sample mean was 31.39. N was 82. Our confidence level, well, we wanted to be 95% confident, so that's 0.95, and then we will calculate that, and that gives us the same answer. Okay, 31.217, comma 31.563. Okay, so not too hard to do. You just have to make sure you're on the right test is all, or the right commands. Okay, moving along. Okay, I give you another question. I'll let you read it. Okay, and then we're going to do a 90 and 95% confidence interval from U. So we're going to use the same formulas up here. The only thing that's going to change in each of these is the 90 and 95%. That's going to be a different Z sub C value. Okay, so there's the answers for those. Okay, and on this one, I just rounded this one to the nearest hundredth for these because it's money. Not a big deal either way, but it's money, so I rounded to the nearest cent. Okay, and we can see as we go from 90 to 95% confident, the only difference is the 1.645 and 1.96. Okay, that's the only difference in those two. And notice what that does. It changes our margin of error from 0.704, so almost 70 cents. It changes it to about 84 cents. Okay, so to become more confident, now we have a larger margin of error, which means our interval will be wider. Our estimate for mu has to allow more possibilities into it, so it's going to be wider. Okay, moving along. Okay, so what happens if you want to increase, what happens in our confidence interval if you want to increase C, the level of confidence? Well, you get a wider confidence level, or confidence interval. That's what I just showed you on the last page. If you increase the sample size n, well, when you go back to the formula, okay, just very quickly, if you make n larger, what you're looking at here, just like with the population proportion, when n was larger, your sigma over square root of n will be a smaller answer. So as n gets larger, the margin of error, the answer there, gets smaller. Okay, so that will make your interval more narrow. Okay, so the basic takeaway from that is to understand that if you want to become more confident, well, you have to allow more values into your confidence level. How do you combat that? You take a larger sample. Okay, so you increase n. So those two kind of balance each other out as you collect a sample. Okay, so now we're going to find a minimum sample size needed to estimate mu. So here we have our margin of error. Now this one's going to be not too bad to solve for n. Okay, you want to get n by itself. So divide by z of c, and then cross multiply. Okay, so we cross multiplied there. And then to get n equals, we're going to divide by e, and then square each side. Okay, so once you divide by e, we would have square root of n here. To get rid of the square root of n, you square it. So after you divide by e, you're going to square that entire side. Okay, so that is how you find the minimum sample size. And again, I'm not going to give you this specific formula, but you will have the value for the margin of error given to you. Okay, and again, you're always going to round up the next integer because you can't find like 12.82 data values. You can find 12 or 13, but not 12.82. All right, so an example of finding the minimum sample size. Okay, I'll let you read that. Okay, so when you go through that, you identify the key values, and we're looking to fill into this formula right here, Z of C. That has to do with your 90% confidence level. Sigma That's your standard deviation of 3 years. E is your margin of error, 0.5 years. To be within 0.5 years of the population mean, that means E, the margin of error, is 0.5, and you're going to square that. So again, it's just plug and chug into the formula, or into the variables in the formula. Okay, a 90% confidence level has a Z of C value of 1.645. Standard deviation was 3. Margin of error 0.5. Okay, so you would need to survey 98 people to be 90% confident that your estimate is within 0.5 years of the population mean. Okay, moving along. Okay, what we just did was we constructed a confidence interval for mu if sigma is known. Now we construct a confidence interval for mu if sigma is unknown. Now in reality, this will be the case that happens in reality more often. Okay, because if you collected all the data values and you know what sigma is, that means you have the population. So you probably would also know what mu is, which means why would you have to estimate mu? Okay, so in reality, that's kind of a contrived problem. Okay, so the reality is the next case is generally what's going to happen. You're not going to know what sigma is. Okay, so if we have an approximately normal distribution, okay, so this is important. We start with a approximately normal distribution or a normal distribution, but you do not know sigma. Then we use a new distribution called the t distribution. Now this is not going to be overly crazy. The margin of error in the t distribution is t sub c times s over square root of n. Degrees of freedom, df for degrees of freedom is n minus 1. Okay, now all the t distribution is an approximation to a normal distribution. The t of c value comes from a table of values, which we're going to look at here in a second. S is the sample standard deviation, just like sigma was the population standard deviation. The square root of n is the same as it was before. It's still the sample size. Different thing here, we have degrees of freedom n minus 1. Now all that a t distribution is, it's an approximation for a normal distribution. So the idea is when you look at graphing t distributions for different n values, as the n value gets larger, so as n increases, the t distribution gets closer to the shape of a normal z distribution. So when n is very small, like say n equals 2, the t distribution may look like this, where it might have a little bit of a hump in the center, but not very close to a normal. What happens is, now let's suppose n is, say, 5 or 10. Okay, what happens is it may look something, and now I know I'm going to not get this quite right, but it may look something more like this. Okay, I missed it. This should be more rounded up there. Okay, it's hard for me to draw that. Okay, so it looks a little more normal. Let's just say maybe n is 10 there. Well, as n gets larger and larger, what happens is we get a more and more normal looking distribution. So when n is large, okay, it may look something more like this. Okay, so there n is large. Okay, so as n gets larger, we get more and more of that normal shape. Now, the theory behind all that is not important for us in this class because we're an elementary class. Okay, but that is what happens, and just be aware that there's a new distribution. Okay, so the t distribution has several of the same properties as the normal distribution. It's bell-shaped and symmetric around the mean. The total area under the curve is 1 or 100% of the data. The mean, median, mode are all 0. Okay, and they're going to be in the center of the curve up here. Okay, just like before. The two new things or the two things to really pay attention to or focus on, are the degrees of freedom, or n minus 1, and we use it when the population is normal or approximately normal and sigma is unknown. Okay, again, that sigma unknown is extremely important. Okay, so what we're going to do is look up in our tables a couple of the values. Okay, so if we have to find a value for T of C, okay, we suppose we want to find a 0.95 or 95% level of confidence and a sample size of 21. We have a new distribution, a T distribution, and we're going to look it up in the back of the book, okay, which I'll show you here in a second. I'm just getting to the page in the book. Okay, and what we're looking at is we're trying to find the middle 95%. Okay, so if we draw that curve, we're trying to find the middle 95%. Okay. Okay, so we have 95% in the middle, which means we have 5% to split between the two ends, or the two tails. Okay, so what we do is we go to our table A3 in our book. Now, it's not, like the math name of it is not table A3, but we go to the distribution for critical T values. Okay, and this table is a little different than the Z's. Okay, but what we have, you notice how it says area in one tail and area in two tails. Well, we had 95% in the middle, which meant we had 5% left over to split between the two tails. So what we have is we have 5% in two tails, or 0.025 in one tail. Okay, so we're looking at that column. Okay, the other thing is, notice on the left-hand side we have degrees of freedom. Okay, it starts at 1, goes up by 1. Okay, and what we're looking at is 5% or 0.05 in two tails with 21 minus 1, which is 20 degrees of freedom. So we're looking for this value, 2.086. Okay, so on that one, we have T is 2.086 with 20 degrees of freedom, and we have 0.025 in one tail or 0.05 in two tails. Now, one thing I want you to pay attention to is that if n got larger and larger and larger, we get this T distribution to be more and more normal looking. Well, notice in a Z distribution, we'd have 1.96 if we had 95% in the middle. So if you think back to when we knew what sigma was, the Z sub C was 1.96. Okay, if you had a 95% confidence level. Well, what I want you to look at here in the table, if n gets large, notice what's happening. Down here at the bottom, 1.960. Okay, so when degrees of freedom is really large, we get the same value that we would in the Z distribution. Okay, 1.645, we saw that before, for a 90% confidence level. Well, trace that up to the top, we had 10% in two tails. Okay. All right, so we can see how that matches up with the Z distribution if n is large. Okay, so the critical value for T of C in this case was 2.086. Okay, in the next example, okay, here we want a 90% confidence level with n equals 14. So we're going to have 13 degrees of freedom, and we have either 0.05 in one tail or 0.10 in two tails. Okay, so we're looking at 0.10 in two tails down to 13 degrees of freedom, 1.771. Okay, so that's where this is coming from. Okay, and I just showed you that as n is large, the z value at the bottom of that column is 1.645. Okay, but we don't know that we have. We didn't know what sigma was, so we have to use t with 13 degrees of freedom. So we have to use the 1.771. Okay, notice that each of those values were larger than the z-score would have given you, which means we're going to increase the margin of error because the t of c is a larger number. Okay, on the next page, sorry, I have paper everywhere. Okay, we're going to construct a confidence interval for a population mean with a sample size of 9, a sample mean of 22, sample standard deviation of 3, confidence level 95%. Assume the population is approximately normal. So as you go through and read this, we pick through the information that we're given. We're given the sample size is 9. We're given x bar. We're given s. And again, this is extremely important. We have to recognize what kind of question is this. This is, we're not given the population standard deviation, but we're given the sample standard deviation. So that means we're using s. And what that tells us, we have to use the t distribution. So we look up t sub 95 if you have 8 degrees of freedom. So I'll just show you real quick in our table. 8 degrees of freedom, and we have 5% in 2 tails. Okay, 8 degrees of freedom, 2.306. Okay, so that's where that's coming from. Okay, and then it's plug and chug into our formula. Okay, except now instead of z of c, we're using t of c, and instead of s, instead of sigma, we have s. Okay, but it's the same concept. Plug the numbers in, and that's what we end up with there. Okay, and then I give you the calculator steps here for the t interval. Okay, so instead of a z interval, we're going to use a t interval because we're using the t distribution. Okay, so you can follow through those same steps. Okay, for the sake of time, I'm going to move on, and we're going to look at number 3. Okay, if you need to pause the video, go ahead to finish that up. Okay, I did have a typo here. That should be is instead of in down here. So we have a hospital reporting that a sample of 20 visitors to the emergency room had a mean, say, of 85 minutes and a standard deviation of 18 minutes. So we took a sample. Okay, so this is extremely important again, is notice they're saying that they took a sample. Okay, so that means when they give us the standard deviation, that is S, not sigma. Okay, so that's extremely important to recognize the difference between when you have to use the Z compared to the T distribution. So assuming the population of emergency stays is approximately normal, construct a confidence interval for the population mean emergency stay for a 95% level of confidence and then a 99. Okay, so I would suggest I think you could probably do this now. Okay, it's a matter of plugging and chugging into the formula. Okay, make sure you have the right T value down here. 19 degrees of freedom instead of 20. A lot of people will just use the N value, but it's N minus 1 degrees of freedom. Do a minute to do that, or I should say pause the video and do that, and I'm going to move on here to the next couple, just for the sake of time. Okay, so number 4, we took a sample of 400 students, and their student loan debt of that sample had a mean of 15,260 and a sample standard deviation of 11,475. We'll construct a 90% confidence interval for the mean student loan debt for all students. So the mean student loan debt means we're trying to estimate mu. Just like up here, the mean emergency stay, we're trying to estimate mu. Okay, so again, it's a matter of picking out your information. Okay, so I'm going to show you the answer here, because all it is once you identify what the values are, it's just plug and chug. Okay, so I'm going to show you the answers here, and then you can look at it and see if it matches up. Okay, the one thing I do want to say is that your sample size was 400, which means you have 399 degrees of freedom. Well, in the book, or in the table, I should say, notice that once you get past a certain value, okay, once you get past a certain value, it starts going up by fives, and then by tens, and then eventually by hundreds, and then 1,000. Well, you use the value that's closest. So 399 is closest to 400, so that's what we use. Okay. Okay, so there is the answer to that one. Okay, and then finally on the last page, okay, this one is a different type of question, because you're going to notice here, I give you a list of values. Okay, so suppose the gas mileage of hybrid cars is normally distributed. The following list represents the gas mileage of several models of hybrid cars. Now, I should have said this was in miles per gallon. Okay, I should have identified that. Not miles per hour. MPG, miles per gallon. MPG, sorry. Okay, so I give you a list of, was it 8 values? 2, 4, 6, 8 values. 8 values. Okay, and I want you to do a confidence interval for the mean gas mileage of all hybrid models. So that means we're looking at mu, trying to estimate what mu is, for 90 and 99%. Okay, so we have a sample size of 8. I give the sample mean is 43.125. Saying, well, gee, Marge, where did that come from? This is why this example is different. Okay, the way you do that is if I give you a list of values, I didn't give you the actual mean and standard deviation. So that's where you go to Stat and Edit. You're going to put those values into list 1. Okay, so we put that list of 8 values into list 1, the 60, 45, and so on. And then we're going to calculate, so Stat, calculate the 1 var stats on list 1. Whoops. Okay, so that's where x bar comes from. And S of x is 10.562. Now notice they do give us a sigma. Okay, now this is where we have to outsmart the calculator. When we put those values in the list, your calculator does not know if those 8 values were a sample or a population. We know that they were a sample, so we're using the sample standard deviation. So even though it gives a sigma, that was only if those 8 cars represented a population, but they don't. Okay, but your calculator doesn't know that. But we do. Okay, so we have those values here. So we're going to use the t distribution, and we're going to have a 90 and 99% confidence interval. Okay, so again, it's just plug and chug once you have those values. Okay, so I will put those up there for you to see. Okay, and again, just plug and chug. Okay, so if you want to pause the video and look at that, you can. The 2 points I'll make is that notice how the T of C value, 1.895, compared to 3.499, meant that to be 99% confident, we ended up with a larger margin of error because of that, 13.066 margin of error compared to 7.076. Almost twice as large of a standard error, or margin of error, when we went from 90 to 99% confident. Okay, and the big idea of all this is that when you look at that 90% confidence interval, Okay, the big idea is if we were to do this process 100 times, so if we were to choose samples of size 8 of hybrid cars and made a confidence interval 100 times, each of those samples may have resulted in a different mean and standard deviation. But if we did that 100 times, we would expect 90 of those intervals, 90% of them, okay, so 90 of those 100 intervals, we would expect to have contain the actual population percentage. I'm sorry, not population percentage, population mean. This one, the 99% confidence interval, means that if we were to do 100 confidence intervals or do that process 100 times, where we chose 8 cars, found the sample mean, the standard deviation, and then did this process 100 times, we would expect 99 of those intervals to contain the true value of the population mean. Okay, so that is the end of the lesson for finding a confidence interval for mu.